Hi, this is Dr. O'Connor. Welcome to Pathways to Chemistry. Here we're asked to determine the enthalpy change for the conversion of 25 grams of ice at a negative 20 degrees Celsius to steam at 115 degrees Celsius. This is under a constant pressure of 1 atmosphere. We're given the specific heats of ice, liquid water, and steam. We're also given the enthalpies of fusion and vaporization for water, and we've converted 25 grams of ice to the number of moles. So we have all the information there that we need. Again, we're converting ice to steam. So what I like to do is sketch a heating curve. And notice on this heating curve, I included the important temperatures. We start at a negative 20 degrees and we end at 115. That means that we're going from a solid to a liquid to a gas. So we have two phase changes here. So since we have two phase changes, I also need the freezing point and the boiling point of water, which I've included on this graph. So let's go ahead and take a look what happens. Remember, in this process, heat is being absorbed. This is an endothermic process going from solid to liquid to gas. So here we start at a negative 20 degrees and we're heating up the ice. And once we get to the melting point, now what we have here is we have a solid and liquid, and the temperature remains constant until all of the solid is converted to liquid. So the liquid keeps absorbing heat, and we're adding heat to this, and until we get to the boiling point, which is 100 degrees Celsius. Now, once we reach that boiling point, notice that this temperature here stays constant. And it stays constant until all of the liquid water is converted to a gas. Once all of the liquid water is converted to steam, sample then is still absorbing heat up until we get to 115 degrees Celsius. That's what the problem states. It could have been 125 degrees, but 115 here. So we're able to divide this heating curve into 1, 2, 3, 4, 5 regions. In this region, we just have the heating of the solid. In this region, the phase change, the melting. In this region, the heating of the liquid. In this region, the vaporization. And finally, in this region, the heating of the steam. We need to find the amount of heat that is absorbed in each one of these regions. And then our enthalpy change then will be the total amount of heat absorbed from a negative 20 degrees to 115 degrees. For this first part, we're going from a negative 20 degrees to 0 degrees. So we're just heating the ice. And we already know, we've done these types of problems, that Q, that's the amount of heat absorbed, is going to be equal to the mass of the ice times the specific heat, and then times the change in temperature, delta T. Remember, delta T is always the final temperature minus the initial temperature. And in this case here, from A to B, we're going from a negative 20 degrees to 0 degrees. So our final temperature is 0, and our initial temperature is 25. So this would be 0 minus, now this would be a negative 20 degrees, a negative 20 degrees. And so this is just going to be 20 degrees Celsius. So now we can go ahead and calculate the heat from A to B. And that's equal to the mass, which is 25 grams, times our specific heat. So for ice, that is 2.03 joules per gram per Kelvin. Notice here, I don't need to convert to Kelvin. This is a temperature difference. And we know that a Kelvin unit is the same size as a Celsius unit. So we can just leave this. Because of the temperature difference between 0 and a negative 20, there's a 20 unit difference, whether it be Kelvin or degrees Celsius. So I'm going to go ahead and put my delta T in here. So that's 20. And I'll just go ahead and make that Kelvin so the units cancel out. So we have 25 times 2.03 times 20. And that gives us 1,015 joules. I'm going to convert this to kilojoules. So I just divide this by 1,000. So that's 1.015. And I'm keeping track of my significant figures here with this line. And this would be kilojoules. Okay. Let's go ahead then and see what's going on in the next region. So here we're going from B to C, and here the temperature remains constant. This is the phase change. Well, we're given the enthalpy of fusion, right? So all we need to do here then, and I'll just put B to C, is we have 6.01 kilojoules per mole. But how many moles of ice do we have? We have this 1.387 moles. So 1.387 moles, and we'll multiply that by the enthalpy of fusion. That's 6.01 kilojoules per mole. Our moles cancel. And let's see what we have. 1.387 times 6.01, and this works out to be 8.34 kilojoules. Okay, so let's go ahead now and see what happens from C to D. Go back to our diagram. So when going from C to D, once all of the solid is converted to liquid, okay, here the liquid is absorbing the heat all the way up here to 100 degrees, the boiling point. So our final temperature is 100 degrees. Our initial temperature here is 0 degrees. So let's go ahead and work that out. So we have 25 grams. And the specific heat for liquid water is 4.18, and that's joules per gram per Kelvin. And then we have delta T. Remember, that's final temperature minus initial. The final temperature is going to be 100 degrees. And the initial was 0 degrees. So this then works out to be 10,450 joules, and that'd be the same as 10.4 kilojoules. So let's go ahead then and take a look what happens from D to C. So we'll go back here to our diagram. We have a phase change again, liquid being converted to gas. The temperature remains constant, so what we need here is the enthalpy of vaporization, and then we'll go ahead and multiply that by the number of moles. So we have 1.387 moles times the enthalpy of vaporization is 40.67 kilojoules per mole, and the moles cancel, and we end up with 56.4 kilojoules. Okay, we've done 4 regions. This should have been from D to E. So D to E. Okay. So let's see. This will be from E to F. So let's go back to the diagram, look at that region. And here, okay, that steam is being heated. And we're going from 100 degrees up to 115 degrees Celsius. So let's go ahead and set this up. The mass of the water, or vapor I should say, and that's 25 grams, times the specific heat for the steam, that's 1.84 joules per gram per Kelvin, and then delta T. Our final temperature is 115 degrees Celsius, and the initial was 100 degrees Celsius. And here we have 690 joules. This is the same as 0.69 kilojoules. Okay, so now we're ready. And all we need to do is add the heats. So AB, BC, C to D, D to E, and E to F. So let's go ahead and add those up. So let's see, this Q here was 1.015 kilojoules plus B to C 8.34 kilojoules. And let's see, here we have 10.4 kilojoules. 1, 2, 3. Am I missing something? Here we have 56.4 kilojoules and then 0.690 kilojoules. And we go ahead and add these up, and we get 77.3 kilojoules.